a postdoc Caltech, work interested in CTF and finding kilonova, gravitational waves in general. So
cool. Thanks, Cecilia, for the invitation. For being here. So yeah, so as Cecilia, I'm Tomas. I'm a postdoc at Caltech working on multi-messenger astronomy. But I'm secretly not really a machine learning person, so I'm here with more questions than answers. So feel free to just interrupt with whatever thoughts you have. So the title of my talk is The Observer's Perspective, because that's me, an observer. I don't really do much AI, but how can AI, or how can I think AI can aid the detection of compact mergers? So the main sort of topic here is heavy elements and where to find them. So that's basically the motivation on why am I interested in this compact merger. So by heavy elements, I refer to this. This is a typical periodic table, right? So you have helium and hydrogen that come from the Big Bang. So this is a colored periodic table, but then you have all these gold and yellow elements that are heavy that we think come from merging neutron stars and dying low mass stars, like that one over there. But this one, the low mass stars die very slowly. So this sort of like process of making new elements, it's very slow. So that's called the S process. But then you have the very explosive merger of stars, that's the R process, because it's rapid. And then this is where I think I call usually these the gold mines, because this is where gold is actually created. So just to going a little bit further, you have here the solar R process abundances. So you have here the atomic mass number, and heavy elements up to like from 70 and onwards, you have different peaks. And we have one confirmed neutron star merger, 170817, but we don't really know if this event was able to produce the exact solar abundance pattern. We know that there's enough mass, but we don't know what are the actual sort of peaks and elements that were created. So our process happens when you have a bunch of neutrons. So this is the amount of neutrons, this is the amount of protons here. So what happens when you have a bunch of neutrons is that you start bombarding the nuclei with neutrons, and then you start growing in size, eventually becomes unstable, and decays the neutron decays into a proton, and then you make a heavier element. So here you have a simulation of what happens after our process nucleosynthesis happens. So you have the abundance of elements here. This black line is where elements are stable, so things will try to go there after this R process ends. So you have here all the elements that were created, and eventually these will go and decay towards the stable valley over here. And that produces radiation. So you have the R process, you have the heating due to the radioactive decay, and that powers the kilonova. So that's basically where I enter this game, because the kilonova is something that you can measure. So you can have a telescope and look into it. What happens here is that the heavy elements they have so many protons and so many emission bands that the optical and UV get absorbed really quickly. So you have here a steep decay. This is for the ones that are not astronomers, this is basically brightness, and this is time. So this is a light curve. So you start having a very energetic and bright object, and this is from the bluest to the reddest. So in UV, it decays really quickly, and then in optical, sort of within 5 days, it decays to magnitudes that's like about like a couple of orders of magnitude. So what's interesting here is that the emission shifts from the optical to the infrared. So you have more, there's more, you have a better chance of finding these events in the infrared. But then technically, it's hard to observe things in the infrared because it's there's a lot of sky background. So it's easier to detect things in the optical, but then how do you detect them quickly enough to follow them on the near infrared? And that's what happened with 1717. So this is the first and only binding neutron star merger that happened, and we have been detected, and we're super sure that this is basically what happened. So I'll start here. So we have the frequency map in the gravitational wave time frequency space. this is time, and this is how fast things are basically rotating. So you start with something that is rotating not too fast, but then the frequency starts going up, and eventually they merge here. And at the merger, you have the explosion, the electromagnetic emission delayed by 2 seconds, and then you have this gamma ray burst, and everything shines and explodes, and it's fascinating because we can actually see them here. So that's basically where, that's basically what happens. So LIGO, it's the gravitational wave detector, gives you this green localization, and from the gamma ray localizations, you have this blue sort of patches, and in the intersection, you have this one galaxy that was 20 days before the detection. There's nothing here, and then you have something that is very bright. So that's 170817.
Can I ask you a good question with that? So you have the image before, where is that image taken? Any time before?
Yeah, this is 20 days before.
Oh, 20 days before. And do you think there's nothing in that image that can give you a hint when you get closer, right?
I guess you could, there probably is some sort of precursor, but it's so random, and this is in the south. So most of the new facilities are coming in the south, like Rubin, probably heard of it. That will give you a more like in-depth analysis for previous activity on that particular galaxy. But for this one, this is the closest we have, so it's only 20 days before. So we don't really know what was there before because it's really hard to resolve. It's really close, but it's only 40 megaparsecs away, but it's still like far enough for us to have like difficulties to see what was there before.
Okay.
Sorry, you said about Rubin, but the events is done, right? So Rubin is not launched yet.
No, it's not.
So it's like, I'm just confused, right? So if the event was just gone.
No. So what I was referring is Rubin will be able to help us deal with that question for the future events. But at that time, the closest in time was only 20 days before. So it will be hard to know at least for this object. Okay, so this thing exploded, and what I wanted to highlight is that you have a GRV. The GRV is a gamma ray burst. It's a very energetic thing that is detected only in the gamma ray energy ranges. So people have been detecting these things for ages. From the 70s, things have been detected in the gamma ray space. So you have a BATSE mission. This is a early 2000 plot. You have a histogram here in duration. So people were like, oh, this is a bimodal distribution. So you have a peak here and a peak here. And then people were, oh, easy. Two populations. One is binary neutrons or mergers, and the other one's core collapse supernova. Easy. We'll separate them in 2 seconds. This is short GRV. This is long GRV. And actually, people were hunting for this optical counterpart to actually see if there's an infrared axis. And you have these 3 events. 130603, 160821, and 170817, and they all show this sort of like infrared axis. So this is the near infrared bands. You have the afterglow, what you expect to behave, but then you have the detections over this the behavior, and you have the same here. You have the afterglow going here, and then you have the detection above what you were expecting. So this is great. We have a near infrared axis. You have our process nucleosynthesis, heavy elements, great. Short GRVs, fantastic. But then 3 years ago, we started finding long GRVs coming from this population, and not like closer to like the border of this. This is like a very long GRV that had near infrared axis. So in this plot here, you have the afterglow of one of the GRVs, and then you have the axis. That's like quite a lot. It's very obvious that there's an axis, and then James Webb launched, so you have images from 230307, and then you have here signatures of tellurium. This is what they claim. They claim that the detection of tellurium was one of the heaviest elements. So we don't really know now because we have examples here and here that could be related to binary neutron star mergers and our process nucleosynthesis, the gold factories. So I guess this is where machine learning could help, because this is just one dimension. This is only duration, right? When you expand this into more dimensions, so for example, if you take the energy peak, people were like, oh, maybe this is where we should start separating things, because this is one block, this is the other block. But then they're also interconnected. These are the kilonova short GRVs, and on red you have the supernova. So they also like span both clouds. So maybe one of the things that AI could do for these finding gold mines is to actually separate them and say which ones are producing heavy elements and which are not. So just to show you a little bit of the data, this is how a GRB looks like. This is just a light curve. These are beams of energy. So you are detecting bursts of gamma rays. Sometimes they're short. This is just one burst that lasts for like a second, maybe two. But then you have a long GRB here that lasts for 10 seconds above the background. So this is, which is really hard to make more inference. This is just like a light curve. It's really hard to say, oh, what comes here or not. And what other things you can do, you can separate it by energy. So you can see here, there's sort of like a shift in the energy. So this is called the spectral lag. So there's a bunch of features that people have tried to put into in order to classify this event. So there's a few papers that I could find about using gamma ray data and doing some sort of clustering and things like that. So into this question number one, finding gold mines in the GRB situation scenario, I think there's a bunch of things that we could do as a community. But then you also have the gravitational wave problem, right? So there are 3 gravitational wave detectors, Hanford, Livingston, and Virgo. They all sort of listen to listen to the gravitational wave in a different way, and then you can calculate the difference in time and then triangulate the signal so you can get a localization. So people have tried to do this in a deep learning way in order to get a more precise localization. So this is not having like extremely successful in the sense that it's very much in the same sort of regime of what we have already. So this red contour is what this deep algorithm did, and then the black contour is what the Bayesian approach does generally. That's the sort of like comparable. So I guess there's still like some progress that could be done in that scenario. And this is where probably would be more helpful, because if you have a more precise localization, you can use the Zwicky Transient Facility. That's the telescope I work with. Because of this extreme wide field of view, it's 47 square degrees, and compared to like other facilities, it basically can map the sky much quicker, right? So it goes up to 20.5 in 3 different filters, and then it's coming entire sky every 2 days. So just to show what it looks like, so you have 16 CCDs. Each CCD has 4 quadrants, and this is an image of 1 quadrant. So you have 64 of these. What we do usually is take this one, subtract from the previous image, and then get transients and things that were changing in the sky. So basically what happens is you take the new image, something over there that wasn't there before, this is the reference image, you subtract them, and then you have this subtraction. But you also have residuals here of like, maybe this is a saturated galaxy, or maybe this is an artifact in the data. So there's a bunch of machine learning that has happened to sort of like try to identify these things. Once you have all of these, you can get candidates, but that's the other hopefully advance in machine learning with this CTF transient factory. When you follow up a gravitational wave localization map, you have all the CTF pointings here, but then you have a bunch of candidates, and sometimes there are too many. So how do you discriminate? How do you classify them, basically? So there has been effort on that end. I just found this is not exhaustive. This is like one of the papers I found. Dan Muthukrishna had this algorithm called Rapid that was trained with plastic LST simulation. So each data point that you feed to the algorithm gives you a percentage, like a classification. So you have sort of like a class probability depending on where you look into the light curve. And that helps tremendously. However, as I told you before, kilonova fade really quickly in the optical. So you don't have 30, 60, 70 days of observations. You just have 3. So how do you deal with that issue? Maybe we can use something like inferencing across the galaxies around. So this is something that Alex has done, calculating or measuring, inferring properties of the galaxies that are surrounding the the candidates, so you can see, oh, maybe this is just close enough in redshift, so it's consistent with the brightness of a kilonova, something like that. Then when you have these candidates, another problem is how do you follow up? So you have 15, 20 candidates, but then you have 3 telescopes and the night is finite. So who do you prioritize and what do you follow up first? So there's reinforcement. I found this, actually I call it one. The reinforcement learning, Miharika Sravan, she's at Drexel. She created this agent that was rewarding the algorithm every time they choose the right kilonova to observe. And it does better than random, but not yet as good as humans in terms of efficiency. So eventually, probably we'll get there. How fast we can do this and how effective are we going to be with our follow-up? And this will be very crucial for Rubin, because Rubin has much deeper limits. So you only will be able to access those sources with really big telescopes, and we don't really have that many of those. So another question.
Can you put more details into this? What really you have done? What are the dates? Is this like a prioritization problem, or can you explain what you?
So this is how to prioritize. So you have you tell the machine, you give the machine a bunch of light years, and the machine chooses which one to get a new data point, depending on the behavior that it sees, right? If it gets the right kilonova or whatever, it will get a higher score than if it doesn't. So you're rewarding the algorithm to get follow-up on the right event. So it probably just learns how to see the light curve, basically behavior. So that's what it's doing. So that's basically what I do when I see the data. So I see 2 data points, and I'm looking for a certain behavior. Usually it's fading, usually it's as given color, maybe looking for a galaxy nearby. Things like can give you a hint of, I have just 1, 2 data points. How can I increase my chances of following up the right source? If that makes sense.
Yeah. Does it also include noises? Like
Yeah.
possibility of noise to the data?
Yeah. It's actually using data, like real data from CTM. The only one that is not really just simulated is the actual kilonova. So it just gives you tidal disruption events. It gives you supernova, so that the agent starts like learning how to separate these concepts. So
Really, the last question. So those like identification of galaxies and disruptions and others, you have theoretical models that how the light curve should look like.
yes and no. So for some supernova, it's really it has been like standardized 1/8 and other stuff like that. But then you have other more stochastic, events like tidal disruption events or AGNs that are hard to model. So we don't really have more data. So what do we do with those? We just use the ones that we have and maybe scale them and keep some noise and whatever. But that's basically what we're doing. So I guess this is one last sort of question that we could probably use. So in order to do this, like measure this near infrared axis here, right? So you have the afterglow, you have the near infrared axis. This is a very pretty exponential decay, just like a power law, but things are not that pretty in reality. So what they have done is like to model this on like this magnetohydrodynamic codes and see how this afterglow is emitting. But this is very expensive to do for each one of the GRBs. So what they've done is to use deep glow to sort of try to derive the energetics, the densities, the environmental properties of the galaxies and the environments, so that we can model the afterglow better. So that's basically the next step into modeling afterglows. And then I just wanted to show you the future. So this will be getting better, but also worse, because then we have more data and more things that we don't know and how to get these things right. So you have new GRB missions. So I put the Einstein probe here. Einstein probe is looking into soft X-rays, But then you also have, this is Chinese European mission, and you have SWAN, that's a Chinese French mission that's similar to GVM, the NASA one that's already active, but it has a soft X-ray component, so you'll be able to see much more in detail the high energy emission. Then you have sort of like the optical UV near infrared, you have Roman that's going to launch in 2027, I think, and then Rubin that's going to start operating hopefully in a year and a half. But that, with that, I guess it's enough for me today. Thank you.
So much, Tomas. Are there any questions or discussion?
Sure.
Thanks, nice talk. So you showed at the end, sorry, I made it late to the, but you showed at the end also some X-ray lighters, and I believe this X-ray afterglows, which sort of depends on what the final product of the merger is, whether it's a rapidly spinning neutron star, things like that. So in some cases, you do expect some sort of flaring behavior in the X-ray. Are those flares happening in timescales that are slow enough to try to follow up on X-ray observatories and help in the classification of these objects?
Okay, so yes and no. Up to this point, I don't think we have the ability to do that. To my knowledge, all the sort of like X-ray flares are archival nature. However, you have now Einstein Probe. Einstein Probe launched in January and it's in commissioning. There have been a few Einstein Probe flares. So this is basically observing the entire sky every day, every 24 hours. So you have a really nice light curve that you can probably measure. So my understanding is that the scale of these X-ray flares, it's about 100 seconds. So you could be able to see one of those with an Einstein Probe, and it's probably a good idea to like go and mine for those in the Einstein Probe data, whenever it's public. But and even if it's, and that would make it another archival detection, but then you probably should set up some sort of algorithm to get the right flare measurement while it's still like flaring, so you can go and look for the optical counterpart with other telescopes. But I believe like it could be possible. How is it gonna happen? I don't know, because there's like a bunch of like data and forces over there. But I think we now have the technology of it.
No one else?
Follow up then. So right now people are starting to think of this multi-model, cross-model sort of AI algorithms where you collect all the possible observations of a source and make some sort of inferences. And I think you did mention about trying to do inference based on what these transients could be based on the properties of the host galaxies, things like that. But are there any expectations regarding what the properties of the sources, of the host sources should be? You know, even outside of the transient event, can you envision a way in which to use, you know, a large collection of data, multivariate data of the particular host galaxy before the transient happens that could really help in the, you know, significantly improve the classification first?
So I guess it also depends on a bunch of physical assumptions that you have, right? So for example, I'm interested in these binary mergers. To get two neutrons that are merging, you need a lot of time. So that means that probably you're looking for an old galaxy. So then you'll probably bias yourself to old galaxies. And what happens if you have a new one? I think it's good to have the entire collection of things because it's probably more likely to get you a detection. But it's probably also good to be open-minded in that regard. So yeah, I guess it's a balance between both.
So I know that like you can sometimes apply like filtering requirements for what you're looking for and just like, you know, that's how you know what you actually want to look at as like human, not, you know, using AI or whatever. Is that not like enough anymore where it's like you have so many things to sort through that you need to employ AI?
I think it's been enough, but it also depends. It varies a lot from person to person. So then you have this study, for example, where to go? that one. So this one, there's a range between like what a human expert,
Yeah.
quote unquote, can tell you about the data, and then it's still like, I would be also very comfortable with like a more concise and precise algorithm that I know how it works and what it's looking for. So this is the score of this galaxy, or this is the score of this transient, versus a bunch of people at 4 a.m. looking through candidates, very tired, and maybe someone missed something, and because that's how the way it works now. And we usually will use a bunch of there's a bunch of people, junior people, recently starting, so maybe you expect them to know a bunch of stuff, but you are not sure if they know or not. So I guess this is more of like how to homogenize the selection of a transient, so we are looking for the same thing. I think you had a question too.
Yeah, it's more of a comment than a question. So when these, techniques are used to select it's important to think how that evolves as that subfield matures, right? Because when you start, it's the Wild West. You're looking for whatever gold nugget you can find. It doesn't matter how you find it. When you find it, you found it. That was a good thing to follow up. But then over time, things change. I'm even old enough that I remember every single supernova being a big deal, right? It's when we used to only have one letter after the day.
Yeah.
And then suddenly you have thousands or hundreds of thousands, or and now the statistical properties that define the sample are essential, and the individuals don't matter. And knowing exactly how you find the sample is really important. And this comes up in like surveys that are going to select this or that type of thing, to follow up with DESI, for example. You can come up with an SVM or random forest or neural net that makes the selection 5% more efficient, and people are like, great, it's more efficient. But now all the things that went into that selection, all the features that are input, when you simulate your samples or whatever, kind of Monte Carlo in your selection things, you have to know all of those things. Whereas if you keep it simple, it's simple. And so there comes a time when anything that complicates the selection really bites you. And so I guess I'm wondering, if you've kind of thought ahead of that transition, like if you're just trying to find the gold to start with, that's great. You can do whatever you want. If it works, it works.
Yeah, I mean, I thought about that too, because I feel like we were very lucky with 170817, that one event was very nearby. It was on a very stereotypically massive galaxy. So everyone's like, oh, that's obviously the one target, and people got it right.
Yeah.
But I don't have a sense of how would that change. So I have the dichotomy now between short and long journeys, for example, which could be like a good example. So 3-4 years ago, if a gravitational wave came with a long journey at the same time, people would disregard the long journey. But now people are going to look for journey. So I guess I look forward to the day that we have hundreds of thousands of but it doesn't really matter. But yeah, it's a good point.
One question online, are you planning to post time windows for O4B and O5 observing runs that trigger follow-up observations in X-ray, radio, etc.?
I guess those time windows are already public. So O4 and O5 are the 4th and 5th observing run of LIGO, and I feel like the community has understood that because it's so hard to pinpoint the source. We need to communicate our findings, so it's usually very quickly that we communicate whatever we have a transient, so people can look into X-ray, radio, and things like that. So I guess we'll continue to happen, and coordination is key at this point.
Okay, I think we can discuss more over lunch, but let's for now thank Tomas again and oh, well, we said that we have more questions.
No worries.
Go ahead.
HDMI.
Here's the speaker.
So next we have Aizhan. Gonna try to pronounce your last name. Akhmetzhanova.
Yeah,
Is that correct?
that's almost
Okay.
correct. Akhmetzhanova.
Okay, and she's a graduate student here at Harvard, right? And she's going to talk about self-supervised learning for astrophysics and cosmology.
Possible for me to still use the laptop?
Yes, yeah,
Or
yeah. So if you just click don't, you're done. Yeah. So you've got a pointer.
They probably nice to meet you.
Yeah.
One second. Thank you. How do I?
It just should come up as a second screen. Yeah, there you go.
Yeah. So, yeah, so the topic of my talk is self-supervised learning for astrophysics and cosmology. But inspired by some recent archive postings on deeper learning in astronomy and multi-messenger astrology, I thought maybe I should instead talk about deeper self-supervised learning for multi-messenger astrology and cosmology. But unfortunately, I didn't have enough time to go through these two papers today, so we'll go back to the self-supervised learning for astrophysics and cosmology, although I feel like someday someone should talk about astrology and cosmetology and self-supervised learning for those, but yeah, next time. So this talk is going to be partly based on this work. Is Sid Mishra Sharma, my advisor for working.
Could you speak up a little bit?
Oh yeah.
Yeah,
Mhm.
thank you.
But just in general, the outline for this talk is first it will give some motivation for the use of self-supervised learning. And then I'm just going to give a very brief overview of self-supervised learning framework. I'll talk about some of the methods that are employed in this framework and the one that we use in our work in particular. It's called VCREG, or variance invariance covariance regularization. I also started because probably quite a few people here work in other areas of astrophysics, like other than cosmology. I will just highlight some of the applications of self-supervised learning in astrophysics. And then I will talk about our particular project, so self-supervised learning for cosmology, and I will focus on a few applications that we explored, such as data compression, marginalization over systematics and nuisance parameters, and also parameter inference with sequential simulation-based inference. And then I will also conclude, but it can be the case that most of the talk is going to be focused on these two parts. Yeah, so we'll see how the time permits. Okay, so for the motivation, current and upcoming surveys such as DESI, Euclid, the Vera Rubin Observatory, and SKA will provide massive amounts of data to probe some of the new and existing questions in cosmology, and making full use of the data provided by the surveys is a challenging task. Also, I just realized this presentation is probably going to be a repeat of my previous presentations for some of the people in the audience, so like apologies for that in advance.
So in cosmology, the way that it's done is, so usually analyzing the raw data is computationally expensive. So it's typically first reduced to a set of some informative summary statistics, and oftentimes those are kind of like physically motivated summary statistics, such as power spectrum or two-point correlation function, bispectrum, and some higher order correlation functions, favorite scattering coefficients, and others. But these summary statistics might not encode all of the physically relevant information from the input data. And it can also be the case that even if the summary statistics, the data vectors might be very high dimensional, depending on the size of the data. So one of the approaches that we decided to explore is to use self-supervised learning with some physically motivated augmentations to address some of these potential considerations. So before I move on to our project, I just wanted to give a brief overview of self-supervised learning framework. So, all right. So in the traditional supervised learning framework, usually a neural network model is trained to perform a specific task, and it uses a data set with some associated labels. However, some of the downsides to this traditional supervised learning is that it's usually limited by the availability of these quality label data sets, which can be quite expensive to obtain or to scale up in some scenarios. And also, new downstream tasks usually require new models to be trained from scratch. So for instance, if a particular data set was used to train a model to do, let's say, some sort of classification, then maybe if you have a task of object detection on the same data set, usually you need to train a new pretty large model from scratch. So what self-supervised learning does is that it combines unsupervised and supervised learning together, and it usually proceeds in 2 steps. So first, the encoder network learns to construct meaningful lower dimensional summaries or representations of the data from an unlabeled data set. And then it uses these learned summaries for a downstream supervised task of interest. So some of the advantages of the self-supervised learning over the traditional supervised learning is that it can make use of the unlabeled data sets, which can be larger in size than the labeled data sets, but makes use of both of them. And then these summaries can be used for a range of downstream tasks, as opposed to just one single predefined task in the supervised learning case. And also recently, some of these methods have been shown to achieve results that are comparable to the state-of-art models that were trained in the fully supervised manner. So there are many different self-supervised learning kind of like algorithms and losses, but in general, this pipeline usually works as a 2-step process. So the first step is the pre-training process. And so in this process, a so-called encoder network learns how to compress an object that it receives, so for example, an image, down to some smaller, like lower dimensional vector that's called a summary or a representation. And usually the way that it's done is that this input vector is transformed into different ways. Sometimes these transformations are called different views or different augmentations of the same object. So for example, in this case, I flipped this image and then I also cropped it and shifted the center a little bit, but the underlying object that's contained in this image is the same, right? So, the encoder network is trained to produce this summary by essentially maximizing the similarity between these different views of the same image. And usually it's done not directly on the summaries, but on the embeddings of the summaries. And the embeddings of the summaries are just projections of the summary into some slightly higher dimensional space by a small network called expander. And it's more of a technical detail. Like sometimes it's also possible to use the summary directly, but it just turns out that adding this expander makes the training better, or it makes the results better.
Sorry, can I ask you?
Yeah.
So are you using a different autoencoder for each of these?
Oh, sorry. So
sections?
I think It depends based on the self-supervised learning method, but for ours, we use the same encoder for both of them. Right. So then once that pre-training step is done, and so in this pre-training step, we don't really need labels. We just need to have some sort of like different augmentations of the same image. That we can kind of like define ourselves. And then once the pre-training step is done, the second step is the downstream task. And usually in the downstream task, these summaries are then used. So these summaries, not the embeddings, are used directly to train a smaller network, such as an MLP, to perform these downstream tasks. Or also, I think in some of the recent work, they show that simple techniques such as KNNs can also work directly on these summaries.
Sorry, a question. So if you don't do these different views and you just do the inference all the way, is this any substantial changes in your final inference parameter, or how essential will be the intermediate step of, just like reset, like shifting the center and just, doing the rotation and other things?
Oh, I see. So I guess if you don't do this step, then it's equivalent to just kind of like the standard supervised learning, right? And this particular, I guess, framework is addressed, is kind of like, but if you just do the kind of like the typical supervised learning, then you again kind of like run into some of these issues where you're limited by the availability of the label data sets. So which tend to be smaller in size than the unlabeled data sets. And also, like usually the fully supervised approach works just as well as this self-supervised approach if the data sets are all the same size. But if you have more like additional data that's, for example, unlabeled, and you want to use it in your training as well to enhance your the performance of your inference, for instance, then it should work better.
Another question, so in an autoencoder, Z and X would live in the same space, right? But here Z is some other space, right?
What is X?
What space does the output of the expander Z live in?
Oh yeah, it's a different space, and it's usually a higher dimensional space than S.
Okay, and how do you enforce that it still contains the relevant information? Because in an autoencoder, you're reproducing an image, of course it contains the relevant information.
Right.
But if you just make up some new space, you still have to enforce it somehow. I mean, for example, the expander could always output zeros, and then Z and Z prime would be extremely similar to each other. So, somehow you have to enforce that the information propagates through.
Right, I guess, so the way that it can be done is by, for example, so I guess like there is no direct way in which we enforce Z to contain the same information about S, but maybe just to like address some of those questions is you usually add some sort of regularization to make sure that Z just doesn't collapse to the same vector for all of the images in your, or for all of the objects in the training set. So for instance, I guess like, yeah, a very natural problem that can occur in this case is that we get a trivial solution in which this encoder just map different input vectors to the same summary. So one of the kind of like approaches to address that is called contrastive learning. And in this case, yeah, I have this kind of silly image that illustrates contrastive learning. So here we distinguish between negative and positive samples in the training data set. And the loss is structured to make sure that the positive samples are pushed closer together, and the distance between positive and negative samples in this embedding space is kind of like maximized, or like that they're pushed further apart. So for example, here the positive pair is the original image and some sort of augmentation of that original image, and then the negative samples are all the other images. So and that's just one of the ways of structuring this contrastive learning. Sometimes so for example, here, it might seem strange that, for example, this dog and this cat are both considered to be equally negative samples in the same training batch. So there are like some other losses that, for example, group this by categories, but still use this primarily as positive examples, but maybe like, I don't know, somehow structure the loss such that these are considered to be more and less negative pairs than, for example, this cat and this dog, or things like that.
Okay, I think that addresses my question. It's most, so I can see this working well for, classification. Are you also going to use this on regression problems?
Yeah, so in our case, we used it for like regression problem. But we used a non-contrastive self-supervised learning approach. So yeah, so contrastive learning is kind of like a subset of self-supervised learning. Here's just like an example loss for a contrastive learning approach called SIMCLEAR, where essentially the loss is a ratio of some sort of like similarity measure between two positive examples divided by just the sum over all of the negative examples in the training batch. And there are a lot of different ways in which this contrastive learning can be implemented. This is a figure from a review by Mark for his company. And it's actually a really nice review of contrastive learning applied to astronomy. I think it was released last year, and they have a lot of different examples, discussion of a lot of these different methods. There are also non-contrastive approaches to self-supervised learning, and this was the one that we use in our work. So this is called VICRAG, or variance invariant covariance regularization. So it consists of, so the loss term in this case consists of 3 terms. The first one is the invariance loss, and that's the term that's supposed to kind of bring the embeddings of the different augmentations of the same object closer together. Then this is the variance loss, and this is the loss term that's kind of like is supposed to address the collapse problem. So it computes the variance within the training batch and tries to drive it closer to some constant to make sure that it doesn't, to make sure that different objects are mapped to different embeddings. And then the third term is the covariance loss, and this one is kind of like trying to decorrelate different features of the embedded vectors and kind of like make them less redundant. But it's primarily this term that's kind of like it's supposed to counteract the collapse problem.
Why is this non-contrastive? Sorry.
Oh, yeah. So
You're still trying to put things that are similar together.
Yeah. I
Things that
think
are not similar far apart.
so.
What's the fundamental difference with the previous loss function that you showed?
Yeah. So in this loss function, the z and z prime only use so in this case, all of these terms are only computed for the positive pairs. We don't really compute this for the negative pairs. So for example, the similarity is only maximized on the positive pairs. And it's kind of like this term that's supposed to do the anti-collapse thing. But it doesn't, like, we don't really distinguish between positive and negative pairs like explicitly in this case. Because for example, here in this loss function, there was like a clear distinction between positive and negative examples. I don't know if that's.
Maybe I'll have to think about it a little bit more. Yeah. Thanks.
Okay, so
Before we move on, can I ask you a quick question? So did you try, or is there any way of doing this while allowing for new groups that, let's say in the example of the squares and another shape, if you look at the embedding space and you see a separate cluster, maybe there's some other class that you're missing.
right, I guess.
Is it worth looking into it, or did you get?
Or like if there's any structure in the embedding space. I think there might be, but I'm not sure if it's necessarily going to be there because, for example, unlike the variational autoencoders, we're not really like explicitly enforcing any structure to be there in the embedding space. So it might just be the case that it will be a bit hard to disentangle what exactly is going on.
But in that case, you would be assigning the wrong label to a new class, right? In your framework, you're assigning labels with self-supervised learning.
Oh, so for the pre-training step, we're not really using any labels. We're only using them in the second step where we're using the downstream tasks. Yeah. I think I might be misinterpreting your question, but maybe, I don't know if that was.
Yeah, we get
is that-
it.
okay. Yeah, so before I move on to like discussing our project, I wanted to just show some applications of self-supervised learning to astrophysics. And recently there's been quite a few works that applied self-supervised learning for a few different problems. For example, the galaxy morphology classification, and also self-similarity search and anomaly detection. And it's mostly for galaxy images. So, for example, this was one of the earliest works that used self-supervised learning for astronomical images. What they did here is, I think they applied this to images from the SDSS. And one of the things that they kind of like showcase in this work is that this ability to use different augmentations is quite helpful because you can also kind of like include your own custom augmentations. So in addition to just like flex or rotation, they also included augmentation that reflected perhaps changes in the BSF function applied to the images. And also, I think they also kind of like introduced different variations of threatening. I'm not 100% sure, but just kind of like making sure that the known systematics or the domain knowledge that we have is applied to the way that these augmentations are created. And then we also showed that by using this self-supervised approach, they were able to get accuracy in their predictions for tasks like redshift prediction or galaxy morphology classification with fewer examples in the training set than just like a comparable fully supervised approach. And then a second one is, so these are just some of the examples. There is actually a lot more, but these are just the ones that I'm familiar with. So this one is called AstroClip, and this paper used contrastive learning to embed two different types of data modalities, the optical spectra and the images of galaxies from DESI into this shared embedding space, and then to kind of like align them using contrastive learning. And what they found is that indeed these cross-model embeddings were well aligned and that they could be used for accurate cross-model searches and downstream tasks, such as predicting physical properties of galaxies, such as their mass and redshift. So, for example, in some of the images in the paper, they showed, like if you, for example, give this, if you do some sort of like self-similarity search on images that are close to this image, you indeed get some. Actually, maybe it's better if you see some of the papers, some of the figures in the paper. But yeah, it's just an example of how these contrastive learning approaches or self-supervised learning approaches can also be used to kind of like encode the data of different modalities together. So okay. I don't think I have a ton of time, but maybe I could just briefly describe some of our work in which we use self-supervised learning for data compression and parameter inference. So we kind of try to extend this approach to include what we call physically motivated augmentations, or augmentations of the data that correspond to the same underlying physics of interest. And we looked at, yeah, 3 different applications. So the first one, yeah, and just to set up the training, we use the VPREG loss. And then our downstream task was cosmological parameter inference. So in the second step of the self-supervised learning process, we trained a small inference network to infer cosmological parameters of interest, their means and covariance matrix, by minimizing the negative log likelihood loss. Okay. So the first thing that we tried is we tried to apply this algorithm on the log normal field, which can be used as kind of like an approximation to the matter density field at late times. So we generated these log normal fields from a linear matter power spectrum, and we did this for 10,000 different cosmologies, in which we varied two cosmological parameters, and then all of the remaining parameters were fixed. And then these fields were just simulated on a grid of 100 by 100 points. So for our, I call it matrix setup or the self-supervised learning setup. What we did for different augmentations or different views of the same object is our same object was the same cosmology, but our different augmentations were the different initial conditions or different initial random seeds that we used for these fields. And we also rotated them to a depth at random. And then our encoder network was used to compress the 100 by 100 maps down to smaller summaries of dimension 16. And then the inference network was used to predict the means for these cosmological parameters and their covariance matrix. And as a way of kind of like assessing how informative the summaries were, we compared the errors that we got on these parameters to the errors that we would get from a what we call a supervised baseline model, which is essentially just a neural network with an equivalent architecture, but the one that was trained in kind of like a fully supervised manner. And what we found is that the relative errors of the cosmological parameters from this self-supervised learning approach were quite similar to the ones that we got from just the supervised model. We also compared the Fisher constraints, and we also found them to be to agree really well for this case. We then moved on to the more kind of like more complicated data set, more realistic one. So we used the total matter density maps from the CAMELS data set. And particularly, we used two different hybrid constitutive simulations, last versus TNG and SIMBA. So there are fewer cosmologies in each series of these simulations. So there's only 1,000 of them, and then we vary both cosmological parameters and astrophysical parameters. So it's a more complicated data set, and it's also a smaller one. So I guess we wouldn't really necessarily expect the self-supervised learning to work particularly well in this case. So we also slightly changed our loss function because of the complexity of the maps. So instead of using just one pair, we would compute it for 5 pairs of different augmentations that correspond to the same cosmology, just to allow the network to learn from more variations. And in this case, our different augmentations were different spatial slices of simulation boxes that were also rotated and flipped in tandem. And once again, we compressed these maps down to lower dimensional summaries, and our inference network was doing pretty much the same task. And here as well, we also found that the self-supervised learning approach was able to infer cosmological parameters with slightly worse, but still quite similar accuracy as the baseline supervised model. So I don't know if I have a lot of time, or if I should.
Yeah, we're out of time, maybe a couple of minutes to.
Okay, so I just wanted to say that this approach can also be extended to marginalize over systematic effects, or to marginalize over some sort of uncertainty, such as, for example, the baryonic effect in cosmology, which tend to modify the power spectrum quite a bit depending on the type of simulation that you're using. So we did this for a very simple toy model of a broken power law, where these different slopes were supposed to kind of like represent different baryonic effects. And we were able to find that indeed these simulations, these summaries contain very little information about the parameters that we're not particularly interested in. And we also used some metrics like distance correlation and mutual information to further analyze the representations or the summaries that we get. And we also extended this to work together with simulation-based inference, but yeah, you can see more details in the paper. So
Is the paper out already?
yeah, it's a paper from last year actually. So yeah. Yeah, so just some of the conclusions. We've explored this self-supervised learning approach for constructing compact and informative summary statistics, and we extended it by including augmentations that correspond to the same underlying physics of interest. And we demonstrated the applications of this approach for these three particular case studies. And however, yeah, additional follow-up studies are necessary before any of this is going to be used in real cosmological data. We used quite a few proof of principle examples, and these are some of the suggestions in how they can be extended. All right. Yeah, thank you.
Thank you very much. Are there any questions? I know we kept interrupting you, so I think many questions were during the talk, but here. Yeah.
I have a quick question. So if you go back to the slide with the campus field, you say you reduced it down from 256 to 128. Did you use an expander network where you compressed it to a smaller dimensionality and then re-expanded out to 128, or is that the full compression?
So this is the compression of the encoder network, and then the expander, I think it expanded it from 128 to something like 4 times this, if I remember correctly.
So I guess I'm still not sure how you train that, right? Because in an autoencoder, you have the input and you match it to the output to train it. But
Right.
here you do not match it to the output.
Yeah, so here you match it to the output in the second step. So for example, yeah, so here you match it to the output in the second step, where you train the second network, for example, and then we'll use to do this sort of like downstream task. So for instance, let's say you have a very large data set with a lot of galaxy images that's unlabeled. So eventually, for example, know, the redshifts of these galaxies or the morphology classes that they belong to. So what would happen in that case is that first you would use that unlabeled data set just to train this encoder, which can then, given an image of the galaxy, compress it down to some sort of summary. And then let's say you have a smaller data set that's actually labeled with, for example, galaxy morphology classes. So what you can do then is you could first get, using this already pre-trained encoder, get the summaries out, and then each summary has a corresponding label, right? So then you would train this downstream, you would train this downstream network to do the, I don't know, like some sort of like classification task. By using the labeled examples, and then classify the unlabeled data set. But in this case, like an additional benefit is that now, because of this pre-training process, the summaries have also been trained on the unlabeled data sets to kind of like learn a little bit more from the data itself, from some of the symmetries that are included in the data.
Okay. Anyone else? Any other questions? I guess we can also chat over lunch. So thank you again, both